All right. I don't know, Jay, if you want to do an intro, or I can also just get started.
Oh, is it me, actually? I did
I
not
think
know
so. That's
that.
what you said.
That's
Oh,
okay.
okay.
Yeah,
I'm sorry.
yeah. No,
Yeah.
don't worry. I had also kind of forgotten to check earlier this week. So yeah. But anyway,
Okay. Um, sorry, I don't have anything to say, so I guess you can just get
Yeah, I'll just start because I don't think I
started.
even told you what I'm going to talk about. But
Yeah.
yeah, basically, I started making a bit of an overview of what we talked about during the brainstorming week. It's in an Excalibur. It looks like a crazy
whoa,
person used Excalibur, I guess. Uh, but yeah, basically tried to put the topics we touched on here, as well as kind of new solutions we came up with, new potential solutions we came up with, which are the gray ones, remaining open questions, which are the red ones, and yeah, just kind of how it's connected. I don't think it will be super helpful to go through all of it right now because that's a lot. So instead, I made some slides on three of the topics, the ones that are kind of the most solid, least controversial ones with the least open questions. And then next week, I can make some more slides on more of the topics, or Niels or Jeff, and we can just kind of work our way through the topics in depth. And then we can also, yeah, kind of come back to this and come back to the kind of gray and red boxes and see if we can make some more progress on those. If that sounds good.
yeah, nice. And sorry, remind me the color. So yeah, red was open questions. What were the other ones? Oh, okay.
So yeah, yellow ones are general topics or kind of facts, statements, like, or things that like kind of features that are necessary, like recognizing relative feature arrangement, even if 3D morphology changed as part of the deformation problem, where voting is split into sharing ID information, sharing orientation information, and sharing location information. So those are just kind of topics slash requirements. And then green are solutions to those. Blue, I just marked some things where I want to do a bit more research in the literature for anatomical and physiological evidence. Those are the least important ones. Gray are the ones that are potential solutions we thought about, but I feel like we didn't quite kind of agree or finalize them yet. Even some of the green ones, we might decide that they are not the right one, but those are more uncertain. And then red are open questions. And then I made the text blue for the ones that were uh, discussed a lot during the brainstorming week in London, just to kind of see what the new parts are that we want to cover to communicate to everyone. Because some parts are old parts, like for example, behavior models. I still just kind of added the main solutions we have there so we can kind of make connections between those to the other problems. And yeah, this is by no means a kind of complete picture of all the problems and solutions. It's kind of the necessary context for what we talked about that week.
Cool.
Yeah, and then I also added comments on some of these, which link to other Excalibur boards where we talked about those ideas before, or in more depth, if you want to look at more kind of detailed drawings of those topics, like I don't know, learning causal associations, layer 3 to layer 1, for example, we discussed it several times before. So I just linked to those there. Um, okay, so yeah, the three topics I picked for today, and we can see how far we get. If it takes too long, we can also just do one or two. Are basically the three main topics we had for the retreat or parts of it. So I have some slides on deformations, um, the kind of partial solution we described with learning lower dimensional models, and then a bit about what's missing and what are potential solutions there. And then some slides on voting, particularly the part of sharing location information, and the potential idea we came with up there. And then some slides on causal interactions, but there I just focused on the affordances part. So I didn't put any slides for this big chunk here yet, because this will be a kind of further in-depth brainstorming discussion more, because we don't really have final answers here. Okay. Let me share my slides. Yeah, feel free to ask questions. So yeah, first one, sharing location information for flash inference, an alternative to voting on locations. So what we currently do in Monty, if we have multiple sensors sensing different parts on the object, each of the learning modules gets one of these locations and features sensed at those locations. They update the evidence with that, and then we do a voting step. And during the voting step, we basically have to, for each green connection here, we have to do reference frame transformations of the hypotheses, of the location hypotheses. So basically take the location hypotheses from one learning module, we apply the sensor displacement between the two sensors that are currently voting with each other to those hypotheses. That projects it into this reference frame, and then use that to update the evidence with the votes and get new evidence values. And it works, but it requires reference frame transformations for every lateral voting connection we have. And for one, there's no anatomical evidence for this. Like if we say that voting connections are basically just associative connections between layer 2-3 neurons and maybe layer 6 neurons, there is nothing in between that could do this reference frame transformation. Like we would have to route through thalamus or some other way to integrate the sensor displacement between the voting columns. And we have this kind of n-squared problem where we have to do reference frame transforms for all of the possible connections. So the current solution just doesn't seem biologically plausible and overly computationally complex. That makes sense so far? Okay. Oh yeah, and just to say, in general, the reason we want to communicate the relative location information during voting is because if we don't do that, we basically just have a bag of feature type vote. So we could just vote on object ID, but then if you kind of scrambled features that are consistent with a mug and each sensor senses one of them, it wouldn't be able to tell that this is mug features but scrambled. So we kind of think that the brain is able to take into account global shape when doing flash inference. So when you just flash an image in front of you and don't have time to move your eyes. And so if we can take account global shape, then there must be some mechanism to share the relative locations of different patches that are getting input.
So
Yeah,
a
and
quick
then
question.
yeah, go ahead.
Yeah, I might have missed it. I'm a little bit so super private. So first, the locations for individual fingers are in their own reference frame, right? And then once we do the RF transforms for every lateral voting connection, what reference frame do they end up in?
So when we get the input to the learning module, they are in a shared reference frame. So like body-centric reference frame or world-centric reference frame. So those are like the XYZ coordinates of your fingers in habitat, for example, or in the world or relative to your body. And then in the learning module, those get kind of hypothesized as potential locations in the object's reference frame. And so then that's the object's reference frame in one learning module. And there we have several possible locations, like we could be on the rim of the coffee cup or at the bottom of it. And then when we send those to another learning module, that learning module is sensing at a different location on the mug. So it shouldn't expect to be on the rim or at the bottom. It should be expect to be kind of offset by this amount from those hypotheses. So we need to apply that offset here. And then kind of combined with the offset, they would kind of think that the eye is most likely on the handle. So that would then, it's basically this transform here is projecting location hypotheses from one object's reference frame to another object's reference frame, taking into account the sensor displacement.
I see. I see.
Yeah.
And it also kind of goes backwards as well. Like LM2 would also send out as
Right.
yeah.
Yeah.
Okay.
So this one just shows one direction here, but yeah, it could also go the other way.
And if you compare it to like voting on object ID, for example, like LM1, when it sends out its votes, each column it sends a vote to, it needs to process it in a different way because there's a different spatial offset and
Right.
so on. But for object ID, for example, it's just sending the same message to everyone.
Yeah.
So the n squared problem, it's not just because it's not like, oh, well, we could just have sparser connectivity or whatever. Like it's the fact that like pairwise we're doing a different transform for each set of columns that communicate.
Got it. Got it.
And when we vote, we send it, we basically tell it to use the same object in the other learning module. So it's like if we're in a cup in learning module 1 and we're sending these hypotheses, we supervise it by telling it that when you go over there, add those evidence to the learning module to the object, the same object.
Yeah, because the votes include object ID as well.
Yeah, and that's maybe a good point that like unsupervised associative learning is almost certainly going to be simpler without this, because we're less concerned about them having kind of learned their internal reference frames with like a similar orientation and things like that.
Okay. Yeah, that makes sense. Just one more question. When we go over to the other learning module, we do some sort of a KD tree over there to find the closest locations because now I'm wondering now with burst sampling, we might have a learning module that has much less number of hypotheses. So we could have a sparser number of sparser hypothesis space in one learning module. So when we do this KD tree, do we add evidence that is like scaled by how far the hypotheses are, or is it just we find the closest one and we just add evidence there? Because the closest hypothesis could be too far from the one we're sending, or
yeah, it's similar to the KD tree with the normal sensor input, that there's a search radius, and if it's outside that search radius, it wouldn't add evidence.
Okay. Thanks.
And yeah, just to clarify, even though I'll talk about an alternative to voting, but that's only to voting on locations. So we would still be voting on object IDs and probably also on orientation, but those two are much more trivial to vote on. Like Neil said, you can just learn associative connections, you can do it all at once. You don't have to do anything different for different column combinations. So yeah, the kind of following slides are really about sharing the relative location information that different sensors sense.
And then, and I was going to maybe just say on this slide, and maybe you were talking about this more later, but one of the other kind of major issues with this current implementation is this is the main reason we are passing locations in a shared coordinate space into columns, and using that as the outputs, and that's what, like, we talked a bit about at the kind of focus week presentation. But that's kind of kept us sort of pegged to this input output, even though we've always felt like displacements would make more sense. And so if we can move away from this, then we can actually kind of embrace displacements.
Yeah. And yeah, I have a slide on that in the end. I think there might still be some issues to work out with just using displacements, but yeah, it would definitely be removing like kind of the main current hurdle for that. Okay, so moving forward, we kind of banged our head against this for about 2 days. The first day we came up with a potential solution that we then discarded on the second day. And on the second day, we kind of wrote down some general requirements of how the solution will likely look like. So one thing we came to a conclusion on is that it will likely have to be a serial solution. So going through the different locations in series instead of being able to do it in parallel. And then also that it likely requires some shared reference frame to avoid having the many reference frame transformations for each column combination to communicate with each other. And then the shared reference frame, this is still an open question where that would exist. So we talked about it existing in the thalamus, in the superior colliculus, in the hippocampus, or in columns themselves through various different mechanisms. And that's still something we need to figure out. We could be learning this shared reference frame. That would be if it's in hippocampus or in columns, or it could be model-free, like this kind of body-centric map in superior colliculus, or kind of a spatial mapping in the thalamus. And so the next, the kind of one proposed concrete solution I'll show is a model-free solution. And so likely thalamus or superior colliculus or some other structure that could represent this common reference frame subcortically. So yeah, here's this proposed solution where we're sensing these 5 locations in space on the coffee mug. Those 5 locations go to the shared reference frame. Imagine it as the thalamus for now. And then each of these locations goes to one of the learning modules that the patch is connected to. That's the kind of standard thing that you all know. Whoops. And then, yeah, each learning module gets one location and then features sensed at that location. So that's the standard thing. They all have a hypothesis now. And so then the proposal would be that after we actually get that sensation, before we move again, we do a rapid replay of all of these locations to all of the columns. So kind of quickly moving through them and sending each location or each displacement between the locations to all of the learning modules, including learning modules or columns that aren't actually getting sensory input at the moment. And so that would mean at the end of this kind of one step or cycle, each of the learning modules has actually information about several locations in the world, relative locations, plus a concrete feature at one of those locations each. And that's a lot of extra information that without voting on locations, they wouldn't have. Without that, they would just have the blue points and can't say anything about the shape of the object. And so, yeah, the idea would be that the rapid replay could happen between physical sensor movements. And then, since that's usually a relatively short time interval, it can only cover a small number of locations, likely the most salient locations that were sensed, maybe 3 to 10, we kind of speculated. Definitely couldn't do hundreds or thousands of them. But then even 3 to 10 of the most salient locations is still a lot of information about the global shape and size of an object. And for the learning module, from the learning module's perspective, that would be similar to basically simulating sensor movement through space without getting feature input. And the kind of bonus nice thing about this would be that this could also be used during learning to solve the shared learning problem. Basically, even though these columns aren't getting any sensory input at all, they still get some information about relative location in space where we're sensing stuff, and they can still be learning something. And that's kind of a secondary problem that's been bothering us for years, basically, of it seems unrealistic to have to expect every column to sense every location on every object they know about. And also the kind of problem of, oh, I can learn something with my hand and then I can infer it with my toe, even though the columns connected to patches on my toe have never actually experienced that shape of the cup or whatever. So yeah.
Question again, sorry. Yeah, sorry, when we're doing what did you say when we're doing the rapid replay, like when we're going through the different points, what is happening, what kind of information is being sent to the LM and what's happening within the LM?
Yeah, so basically we would send the locations, these 5 locations, to the learning modules. If you notice, so on the first step, when we actually got the sensation that each learning module is connected to, we also got features.
Yeah.
We got features and location and orientation. At the next
like
5 ones,
normal.
we probably just get locations. So we wouldn't get any features. Probably also no orientations. And yeah, and so the learning module can still do quite a lot, or the column can still do quite a lot with several relative locations. If you remember in Monty, features are kind of lower class citizens to locations, like the shape of an object is more important than the color of it. So it can still help us a lot with inference and especially determining the rough size of an object or what kind of object it could be.
Right.
Yeah.
So basically it can lay down points on our object model, even though that point itself doesn't contain any feature orientation. But,
right.
Even if we do that, like we can still get the overall kind of morphology, which is incredibly useful.
Exactly. Yeah.
Okay. And then the ones,
Yeah,
with the LMs that are not getting the input. Oh, so these are LMs that are not looking at the cup, or are they? At first, I thought they were parent LMs, or are
no,
these
sorry.
just?
Yeah, I didn't have more space, but those would just be
Okay.
columns like, I don't know, on your palm or on your toe or whatever that are not actually currently sensing the cup, but they're just they can still learn the
Perceive
model.
location. Okay. Sorry, Nils, go ahead.
Yeah, I was just going to say that part of the kind of, I guess, not getting feature inputs. I mean, maybe we can find a way that biology could do that, but assuming we can't, then part of the importance here, and also of there just being a few points, is that these would be kind of salient points of some kind. So, whatever these 5 points are, firstly, they're on the object. They're like sensing something. It's not just like sensing nothing. Those columns aren't going to be kind of sharing information, and there's going to be kind of a preference for ones that are kind of sensing interesting stuff. So again, if you're laying down a point, even if there's not any information there, it's kind of like, okay, this is a point that's important that we're going to come back to a lot.
Yeah.
And then and then I thought I'd just mention, like, there's an interesting biological analogy that kind of supports this as well, which is hippocampal replay, which is where both when animals are asleep and also when they're awake and kind of thinking, they have this rapid replay of like spatial sequences, like how they've been navigating through a maze and stuff. And what's interesting is that takes like 50 to 100 milliseconds to happen. And if you look at like perception, we saccade about 3 times a second, maybe maximum 5 times a second. And like rats, when they whisk, that's at a rate of like 5 hertz. So it seems like there's kind of a lower limit on how quickly we move from one percept to another, or like from one kind of input of multiple things to another. And the timing seems to fit with like how long, if the hippocampus was involved, it would need to kind of replay the spatial sequence before we then kind of do the next saccade.
What did you say was the timing for the hippocampal replay?
So 50 to 100 milliseconds.
Okay, so
And
it's
I think
faster
it's
than the
similar.
perception.
Yeah, exactly. So it's faster. So the idea
Yeah.
is it could happen within that gap.
Right.
You look at something, this replay happens, and then you have a bit of time before you then look at something else. A replay happens, and yeah, I think the replay tends to be also kind of a similar order in terms of the number of like elements in a sequence that it's replaying.
Gotcha.
Something like kind of 5 to 10. It's not hundreds or thousands, and it's not just like one or two.
Yeah. Is there significance for the green line? Just out of curiosity, the one that goes vertical.
It's just because I copied this from a figure from our documentation,
Okay.
and that's
Okay,
the
okay.
voting connection.
Yes, I guess
Oh,
that's
okay.
classical. That's classical voting, which would still
They're still voting on object ID.
Right. Okay.
Just one question. It's unclear to me what decides the order of the sequence, because I mean, we're thinking about this as like flash inference, or it's not like hippocampal replay where you'd go through a sequence of observations and they have a specific order. But if you have all of these are just doing flash inference at the same time, there's not a specific order that they go through. Is there like any rule that we should follow about which ones to start with first and then go, or is it like based on which sensor observed first, even if there's like a few milliseconds between them?
Yeah, that's a good question. I mean, it seems that like from the learning module's point of view, it shouldn't matter in which order it gets that sequence. But I guess mechanistically, how this one decides in which order to replay it, I'm not sure. It might be, yeah, just randomly in which order it saw them by slight temporal offsets, but or just neighborhood or some basic heuristic. But yeah, I'm not sure. We'd have to kind of go back into the literature more.
I'm sorry, I'm joining late. Guys, can you hear me?
Yeah.
I thought this is
Morning,
one of
Jeff.
the morning, morning everyone. It's funny. I had this on my calendar. On my phone, it says it's 9 a.m. On my laptop, it says it's 8 a.m. So who knows? So sorry about that. I don't know how that's possible, but here we are. I thought this is one of the sort of the weakest of the things that came up of maybe that week. But I think what we reached the conclusion, I'm just jumping in, hopefully I'm not like misspeaking here. We kind of concluded it has to be done serially. That was sort of the conclusion. It wasn't possible to do this in a parallel fashion. And so we're looking for potential solutions serially. And this one had a lot of questions about it.
And this is
Yeah.
motivated by reducing this n-squared requirement.
Well, it's required for inference. No, it wasn't. Let me remind myself of this. It was definitely required for learning, n-squared problem learning. And in fact, it's just that we can't possibly train all the columns, even in V1, on all the different things. It's just too many, possible permutations. So yeah, I'm trying to jump back into it again. This also, I think, is also required for inference too. Or do we have another solution for inference?
No, yeah, this is about inference. It's about flash inference.
Oh,
So
well, it's inference and learning, right? The same problem.
yeah.
Yeah.
Right.
Well,
Right.
yeah, this particular solution could also solve the shared learning problem.
Right. All right. So again, I'm sorry for jumping at the last moment here. But anyway, this was the best idea we had that dealt with this sort of serial processing requirement. And so it's not a solid, it's not like a confirmed, but this is the best one we came up with.
Yeah.
Yeah, and maybe one. Go ahead.
I was going to say, I mentioned earlier that, yeah, we concluded it has to be a serial solution. It requires some shared reference frame, but there's still uncertainty about where that shared reference frame would be. We listed several options and whether it's learned or model free. And yeah, so this is a concrete description of a potential implementation, but still not concrete enough to kind of say where would this shared reference frame be, what mechanism would replay these locations. So it's still a bit conceptual, but it would be concrete enough to implement it in Monty, I think, but yeah, not to describe it, how it works in the brain.
Right.
Yeah, and then I was just going to comment on the kind of model free versus learned or whatever. at least the way I was thinking about it, I feel like it's more, it just needs to be like a reference frame that acts as a buffer. Um, so like it could still be the hippocampus. I don't know if it's necessarily like learned. I guess it would be like temporarily stored, but it's not like this is relying on long-term models,
Yeah.
even if it's happening in the hippocampus. But maybe that kind of reference frame buffer kind of could be, yeah, in a kind of subcortical structure that just, like you were saying, like the superior colliculus just kind of lights up certain regions and it says, okay, these are where we're going to replay or whatever. Um,
Yeah.
Question.
I think what Vivian just mentioned importantly is that we have a way of implementing this in Monty, even though it probably won't be exactly the way the brain does it. But still, it was clarity, thinking like, my gosh, we couldn't think of a way that this works in parallel.
yeah, like we could for sure share the input features in Monty. Like we could pass those around, which would make the learning more shared. But of course, like if we're going to do that, we could also just clone models from one learning module to another. So it's I guess
Right.
finding that, you know, and but also not going down the path of like, okay, well, if we start ignoring
But
the brain entirely, then we might get confused about.
but I mean, even sharing features in Monty, I don't think it would make that much sense if they go to learning modules that get different types of features, like touch versus vision models. Like the touch model can't do anything with the color information from the
Yeah, but
eyes.
more like morphological features.
Yeah.
I think Tristan is Jose. Yeah.
So my question is, how does shared, like, is it a requirement that what shared RF replays is the same object, and how would it know?
So yeah, they would have to be another mechanism to have an attentional area specified around that object. And we only replay locations in that attentional area. And then I guess another thing I didn't put on the slides, but I put it in here, was, sorry, that, yeah, all columns in a region have a reference frame for the same object active, even when they are not getting any input, which I thought, yeah, would be a nice way if it is that way, but it's an interesting new way to think about it, that like even the columns that are not currently getting sensory input still have a reference frame for the coffee cup or active, and they're still able to kind of process information that is being sensed in the attentional region that they're currently not covering.
Yeah, just on that topic, sorry, Dale, before, it's just that, yeah, for those who have been following kind of our discussions about out of model movements, what was previously called out of reference frame movements. So there, the idea was that, like in our most recent thinking before this retreat, we were thinking if you move out of a model subject to like a short time window, your hypotheses would be kind of thrown away because it's like, okay, well, now you're no longer on that object. I guess the idea here, I'm still, I guess, kind of 50-50 with what makes most sense. But the idea here is kind of like all of the columns in the brain are sort of attending to the same thing at the same time. So if you're looking at a mug, kind of any column that knows about a mug will be thinking about a mug, even if it's not on the mug.
So did we? I don't know if we talked about this. This came up on our last day at the retreat. The issue of the sort of the parallel hippocampal and cortical models. And one of the ideas we had there, I assume you haven't talked about that yet this morning, right?
No.
Okay. One of the ideas there we had there was that the object ID is sufficient to invoke the anchor the correct reference frame for a column. And so that's what Niels was just talking about. But we came up again in a different context between the hippocampus and the cortex. But the idea here is if a column is getting it's seeing a pattern on its apical dendrites, which is the object ID, that it acts like a seed, which would anchor the reference frame uniquely to the object ID. So I think that's related to what that we came up with that later, but that's related to what Niels was just talking about. That if you can imagine all the columns in a region are sharing the same, there's an object ID that's spread across all these columns. even if the column's not getting any input, but it's there, it's up, and it's broadcast across layer one. And that is sufficient to tell the column, oh, not in a learned way, but in a sort of seed way, that you should anchor. You could anchor your grid cells in a certain in a particular way, and so the object ID itself is sufficient to invoke the correct reference frame. I hope I'm not speaking out of turn here, but that was part of the solution we came up with in the hippocampus.
Yeah, and I mean, it's nothing new that the object ID would invoke the reference frame of that object, but just I think thinking of it in this context, clear, yeah.
Well, I think what's new for me is that it would do that even if the column's not receiving any input.
Right. Yeah, I think that's the main point
that was the new
trying to
point.
make.
Right,
Yeah.
right. That's the new point. In the past, we'd say, oh, a column's getting input, it's not clear what it is. The object ID comes in on its layer one and says, oh, this is the object you're supposed to be observing, and it knows what to do. But we're saying, yes, it comes in even if the column's not getting any input at all. It'll essentially lock on. And so as Niels was saying, even when you're moving, even if the column's off the object, it'll know where it is on the object in some sense.
Right. Yeah, Dale.
Oh yeah, I was going to jump back. Thank you for that slide change to the sequence of replay. You mentioned before salience is important here. So wouldn't perhaps sorted salience order be a natural way to replay?
Yeah,
and then you
that's a
could
good
have a
point.
cutoff that says I'm only going to play at most 5 or something.
Yeah. Yeah, I think that'd probably be the most natural thing to do. No, I don't know why I didn't think of that, but yeah, that makes sense to start with the most salient and then see how much you can get in.
Right. I don't know if you mentioned that, but in the brain, you can only do a few of these in the time frame allowed.
Yeah.
So you wouldn't be able to go, you show 4 in this image, that's a good guess. 4 or 5, something like that. So it's not a perfect universal solution.
Yeah, no, I'm curious, maybe this was what you were going to talk about later, Vivian, but here you've been kind of using the language of locations being passed. Is it kind of an issue? Because it seems if we're storing, are we storing displacements? And if we store displacements, then it gets kind of hairy if we start passing those all in. So is that maybe why?
Well, we would always be storing locations, even if we send in displacements, because it's locations
in the buffer.
Space. But
right.
For one, I didn't want to make 2 conceptual changes in one slide now, and I just want to stick with the way we've been thinking about it so far.
Yeah.
The way it is in Monty right now. But yeah, my next slide is basically how it would look like. There's one extra thing we would need to do if we only passed in displacements instead of locations in that shared reference frame. But yeah, maybe Rami, if you have a question first.
Is there a difference between the shared reference frame and just an egocentric reference frame, or why we're making that distinction?
No, egocentric would be a shared reference frame.
Okay, so we could use egocentric for all these sensors.
Right.
Yeah, it's more just that it's a buffer that kind of stores them until the replay is done.
Yeah, but it has to be a shared reference frame, and the buffer needs to be using a shared reference frame to store them, and that could be egocentric reference frame.
Okay, but we don't have to create a new reference frame for it. We could just use whatever egocentric.
Yeah, and it's not like object specific or anything.
Okay, yeah, okay, good. Thanks.
Any other questions?
Just like a small quick one. When you mentioned the timing for the saccades, did you mean microsaccades?
No, normal saccades.
Okay.
So,
do they have approximately the same timing? It's just that microsaccades move in a smaller angle or smaller amplitude.
Microsaccades, I don't remember, but saccades, I'm pretty sure it's 3 to 5 times per second, like every 200 to 300 milliseconds.
Okay.
Microsaccades, I think, are more frequent because they tend to happen after you perform a saccade.
Gotcha.
And it might have multiple.
Right.
Yeah. Okay. That was it. Yeah. Move on.
Okay. So then, lastly, to the question of does this remove the need for communicating locations? So yeah, since we don't need egocentric locations anymore to convert location votes, Monty today could switch to displacements if we use this solution. So yeah, right now, the main reason we are sending locations to all of the learning modules instead of movements or displacements is because we need the absolute locations in the shared reference frame, in the egocentric reference frame, to be able to convert the votes, the location votes. If we don't have to convert location votes anymore, we wouldn't need to send locations anymore. However, when replaying displacements, we would have to calculate a different first displacement for each sensor that actually received input. So basically, we can replay the sequence, but at the very first step, when we actually moved and got the actual feature input, each sensor is in a different location in the sequence. So if we started here, we can't just afterwards replay the sequence of displacements. We have to calculate a displacement to the first salient location and then go from there. I don't think it's a huge issue, but just something to
It's a
bring up.
complication.
Yeah, it's a complication.
Did we discuss that with the research offsite, or is this a new idea?
No, I just
No,
thought
I
of
think
that
we
when I
didn't
was
get to
putting
it.
together
Yeah.
the slides.
Yeah. Again, I feel like the actual solution we came up with is the best we could come up with, but marginal in some sense. But it was, but again, that insight that has to be done thoroughly seemed to be solid.
Yeah. So yeah, I mean, we would still have location representations in this shared reference frame. We would still have location representations in the object-centric models. We could send displacements between the two and not send locations to the column or learning module. But yeah, then this space has this kind of additional requirement to have to calculate the displacement for the different sensors differently. It's an open question, I guess. Again, in Monty, this would be easy to calculate and do if we wanted to switch to that in Monty. Secondly, to me, I haven't thought it all the way through in my head yet, but another thing I feel like we would need to think through if we switch to communicating displacements is whether the action outputs need to know about egocentric location of the sensor, or again, if we can use a solution like we talked about during the week, where the kind of egocentric location representation is kept subquartically, and then the column just sends displacements, and then subquartically it figures out what location in egocentric space to move to. But yeah, it's just another kind of question mark I would need to figure out first before we decide to switch to communicating displacements. Yeah, basically the kind of layer 5 conversion back to egocentric space, whether that needs to have information about egocentric location of the sensor. Okay, that's all I have on the communicating locations topic.
Yeah, a quick question for me. What topics did you talk about before this?
So I basically just I put together kind of a mind map of all the topics we talked about during the week. I didn't go through this in detail, I just went through the legend for it. And then for today, I prepared slides on 3 topics, the ones that I felt were the most concrete with least open questions.
The one we just, the first one is the one we just talked about.
Yeah, exactly. The first one is one we just talked about, and then I have one on.
It seems like there's a lot of open questions, but what the hell?
I didn't say no open questions. I mean, all of them have, so the red parts are open questions. So each of the topics I'm presenting today also have open questions. But it just felt like if I went into like this area of the map, it would be like all open questions. So
all right. Okay, thank you. So I didn't miss too much. Just the first one.
Yeah, no. And so yeah, the other 2 topics I have slides for today are object deformations and affordances. And yeah, we can see how much we get to. Okay. Then, yeah, if you're ready for another topic, we can move on to that. Okay, so object distortions. I'll present the kind of partial solution we talked about, plus talk about what is not solved by that and what are kind of potential additional options we talked about. So yeah, the problem is we want to recognize relative feature arrangements even if the 3D morphology has changed. So like imagine a crumpled sweater with a TBP logo on it. We still want to be able to recognize the logo and the sweater if the sweater isn't perfectly flat on the ground, or a cable. The cable could be in basically infinite 3D configurations. We're still able to tell that this is a cable. However, our models are static, they're rigid models, and so it's unreasonable to think we can learn a rigid model of all the possible configurations of the cable or all the possible configurations of the sweater, and recognize them all that way. So there needs to be a different way to do it. That's kind of the problem setup. Does that make sense? Okay, and
And
so
just an observation about this, if you don't mind. It turns out, obviously we were able to learn rigid objects, and that was essential for figuring out most of the theory. But in the real world, there's very few rigid objects. In the natural world, I should say, the natural world has a lot of variability. So we've, by focusing on rigid objects, we're really focusing on largely human-made objects. So we had to solve that. But this is more than just like a corner problem.
right,
This is the way nature is.
yeah, it's a very very important problem. And so yeah, the solution is actually quite powerful, I think, and covers a lot of cases like the cable and the sweater, which is to use movement in lower dimensional space instead of movement in 3D physical space. So one example, Jose has already been working on implementing over the past months, which is a 2D sensor module. So in this example, the sensor is moving in three-dimensional space, like your patch moves over the sweater in three-dimensional space and is sensing three-dimensional locations and movements. But then what gets sent to the column or the learning module, would be movement on the two-dimensional surface space. And so on the surface, you can't move arbitrarily. You have to stay on the surface. So you can only move up, down, left, right, diagonally, but you can't move in and out. So you have one less degree of freedom, and essentially moving on surface space means that your representation is invariant to any kind of 3D distortions. And similarly, with the cable, we could even move in 1D space, so moving forward or backward along the cable. And if we only move forward and backward along the cable, that remains completely invariant to any of the possible 3D distortions the cable could have. And so to just make it a bit more concrete, I made a couple of example animations. Hopefully that makes it more clear. So in this picture, I'm showing what's being sensed in the world. So we have a cup and we have a sensor patch, the yellow thing here. And we have two sensor modules. And one of them is the kind of conventional 3D one. It sends the 3D location of the patch to the model. And so we get an XYZ location in the model, lay that down here. The 2D one only sends two coordinates, X and Y. Z is always 0, which doesn't exist. And so moving along surface space, we can only move like up, down, left, right, like I mentioned. And so we also lay that point down here. That's the 2D model being learned here. And so as we move over to the right, we move in three-dimensional space, and that would look kind of a bit curved because the cup is curved. We move outwards. But on surface space, we just moved right, straight line to the right. And so that looks like that. And as we kind of move towards the right on the cup, the surface model remains perfectly straight. We're always moving just to the right along the surface, while the kind of 3D model models the movement in physical 3D space, so the curvature of the cup. And because the surface model kind of abstracts away the curvature of the surface, it only represents the movement along the surface. This will match the Thousand Brains project logo, no matter if it's on a flat surface or if it's on a curved cup or if it's on a wrinkled t-shirt. Any of these configurations, it will still look exactly the same. The input locations will look exactly the same if we're moving left to right. And so you're able to both learn and infer this kind of Thousand Brains project logo on any morphology. And then to another example, the cable, taking away another dimension. Oh, well, okay, that's not correct, but it should be, let me correct this real quick. It will not be correct in the following slides, but just to make it clear, the action space here is just forward and backward. You can't move up or down or diagonally along the cable. So we basically just have an X and it's just positive or negative direction. And so as the patch moves along the cable in kind of three-dimensional space, it has this wild shape that we could never hope to match to any previously seen cable morphology. But in 2D space, where we're always just moving towards the right along the cable, or just moving forwards, it's just a straight line. And then I just marked this one purple because the input feature might also be like a child object ID. And for example, here you could recognize the end of the cable, the plug, and that might be a more specific feature that identifies the type of cable. So yeah, to kind of write it up, learning and inference uses the same type of movement input, or would need to use the same type of movement input. So like we wouldn't learn with the 3D sensor module and then infer with the 2D sensor module. Learning module or cortical column doesn't need to know what type of movement input it receives. So there's absolutely no change in what the learning module does. The only thing that's different is how physical movement is processed or represented and sent to the learning module. And then additionally, we might need some specialized policies to follow along relevant dimensions, for example, following the cable or following the seam of a shirt or the edge of a blanket. And then
Yeah,
lastly,
I guess the principal curvature policies might already be a pretty good starting point for that.
right, yeah.
Because yeah, like the seam of the shirt and the wire and stuff will kind of
Yeah, right. And then yeah, compositional models could also be used to recognize distorted morphologies, like the crumpled t-shirt itself, instead of, before I showed the logo on the crumpled t-shirt. But if you just want to recognize the crumpled t-shirt itself, here's another example. Let's imagine now we have another learning module in between here that recognizes kind of, or even the sensor module recognizes some specific features on the t-shirt, like the collar usually looks similar on t-shirts. So we learn the collar, and then our policy moves us along the outline of the shirt. We would notice, okay, relative to that is the sleeve, and then relative to that is another sleeve feature, and then there's the seam, and then there's the bottom. I'm sorry, I messed up these slides. This should say 2D, but and then relative to that is more of the bottom of the t-shirt, which again has a distinct kind of sewing normally on t-shirts, a seam and sleeve. And so you can get kind of the sequence of the relative of those kind of t-shirt specific features, and model them that way, and still recognize it as a t-shirt even though the morphology itself is crumpled. And again, you would want to use kind of a policy that goes along the outlines of the t-shirt, for example.
Is that an English way of spelling sleeve?
Oh, I don't know.
Oh, okay, okay. I thought that was some kind of British
You're
thing.
right.
Okay.
It's yeah.
And maybe you're right,
Apologies.
and I'm just like, maybe this
No,
is like,
no.
okay.
The US did double E, right? Right.
Yeah, yeah. Okay. I'm good. All right.
Wow.
I think this is a
Um,
nice solution. It feels like it doesn't require us to see the t-shirt in a flat form first, because we could follow the curvature or follow the so we don't need to see the canonical form of something, or like if we're looking at a cable that's all tangled up, we don't need to see it all stretched out.
Right.
right.
Yeah, exactly.
I thought this was one of the more powerful things we came up with. And I'm not sure how novel it was, because I don't know, Jose, you're working on some of this already, so I don't know. But it was definitely felt like, yeah, this has felt really good when we did this one. And we went through
Yeah.
a lot of examples. This works with both touch and vision, right? If the t-shirt is so crumpled you can't follow an edge or seam or something like that, then all you have to do is rearrange it enough that you can, right? It doesn't even have to get in the canonical form. And then you can do it in the dark too. I use this example a lot. When you pick up a crumpled t-shirt in the dark, you find a feature, and then you just sort of run it through your fingers, trying to find, follow it along to the other side of that feature, like get the other side of the collar, and then you hold it up, and then you can, then you have it in a canonical form. And the same with a cable. If you have a cable and you want to plug it in, you might pick up one end of the cables, because there might be a bunch of cables that you can't tell which is which. Then you just blindly, you don't have to look at it even, just run it through your fingers and pull it through your fingers. And you're basically doing that linear movement along the cable. And you have a sense for where you are in the cable as you do that. You know how far you've gone, and you expect to hit the other end of the cable at a certain point. So it really seems like a pretty good idea.
Yeah. Yeah. I think it's definitely a very powerful solution that's pretty simple to describe. And yeah, definitely it solves the t-shirt problem, it solves the cable problem and all of its variations, which is great. And then yeah, unless there are more questions on this, I can go to the one part that it doesn't solve.
Okay. I guess, yeah, it's more of a comment. Like,
Yeah.
I think because I've been working on implementing this, I thought about why this was powerful. And so I think the kind of true benefit that, the 2D SM, or, doing this, learning this kind of representation, is that it learns something so I guess in math vocabulary, it preserves intrinsic geometry. Like, we're learning something intrinsic about the object, regardless of kind of something external, compared to point clouds. And I think having that kind of intrinsic representation of an object is very useful, to be invariant to various things.
When you say the intrinsic representation, what do you mean, Jose? What is it? Is it like the canonical form of the t-shirt, or
No, I mean, again, mathematically, it means that kind of distances between objects are preserved. Like,
okay,
yeah.
So you
So
mean the distances between letters
the
on the
features?
logo?
yeah, distances between features are preserved.
Yeah, so
Yeah.
like the lower
Maybe another way
dimensional
of
space
saying
is
kind of
still
invariant.
Yeah. I mean, there's like a whole field of mathematics on this. Like,
Yeah.
the whole way that we have implemented this is kind of based on that.
Well, I don't know the mathematical definition of intrinsic, so that's why I ask. 'Cause I have the everyday understanding of intrinsic.
That's it. I mean, maybe you'll get to this on the next slide. Like, I think there's like still few cases where this would help recognizing many of the things that we discussed, like the crumpled t-shirt and the cable. But yeah, I think there's still a few cases where it will not be able to do so. But I think it's becoming more.
We should get to those in a moment.
Yeah.
But just,
Okay. Let's just get to that.
Well, but just hearing this again now, following on the comment I made earlier, that the world is actually full of deformed objects, right? Trees are not. There's no tree is identical. They're all different. And so we have this sort of a canonical model in our head. And same with the t-shirt. We all draw a t-shirt similar in this little printed 2D cartoon-like way. But this gives you a way of, I think just thinking here gives you really a way of understanding how we deal with classes and, like how do you recognize a tree? And we've tried to use these ideas before, but the idea that you might have to follow the edges or follow you might have to do this dimensionality reduction movement process to see something, a novel thing, and say, oh yeah, it's the same as my canonical form of it. So I think this is going to turn out to be a very general solution to almost recognizing anything. If it's not in the classic canonical form, then you have to do this.
Yeah,
I guess
it's nice because learning modules remain exactly the same. And we're still working with metric spaces. I think maybe that's what you also said, Jose. Like the 2D models are still metric spaces. We just abstracted away the dimension in which the distortion is happening. But we still keep the relevant dimensions to recognize what we want to recognize. So the relative arrangement of features of the t-shirt in kind of surface space or 2D space, or of the logo. And so, yeah.
Besides examples of like when this would work, which are kind of more like, I think the biggest thing is that we're not going to have, are we going to have orientation for distorted objects? Like we cannot really recognize, I think that, so let's say this helps us identify the ID, but
right. That's an interesting question. What's the orientation of this picture of this t-shirt? Or what's the orientation of the cable we saw in the previous?
No, we can do orientation in the lower dimension. So that like the collar sleeve and all that, we can, once we infer what it is, we can orient the lower dimension model.
Right.
Or child models even. Like we have a clear sense of the orientation, at least of the collar.
Well, that's right.
Or like the tip of the cable. But what is the orientation of the cable as a whole? It doesn't really have one.
Well, I don't know. It's interesting. Just take the t-shirt again. I've been so fascinated by how I can manipulate t-shirts in the dark and put them on. And it's just an interesting problem. I can just imagine. I'm trying to come now. Let's say I'm running down the side of the t-shirt from the sleeve, and I want to get to the hem at the bottom. At that moment, I have an orientation of the t-shirt on the edge I'm following. I can imagine, it's horizontal or some skewed angle, but it's not vertical because I'm pulling it sideways. And so, in some sense, I do have an orientation in the lower dimensional space. And that orientation changes as I manipulate the object. Like if I now get to the bottom of the t-shirt and I flip it upside down, well, now the orientation of the t-shirt, the part that I'm holding it defines the whole thing. So I think there is an orientation, although it may be restricted to the part you're observing at any point in time.
I mean, so it's not an orientation of like the whole thing. I mean, but
no, you can't. You can't. You can. Go here.
I mean, I would put it like Rami said. We can infer the orientation in the lower dimensional model. Like for example, with the cable, in the 1D model, it can only be forwards or backwards. It can only have the USB plug on this side or on this side. And we can't infer that until we get to to one of the ends of the cable. But once we get to one of the ends, we know which way around the 1D model is, and we know what side we're on and what's on the other side if we followed the cable backwards. So I think in that sense, in the lower dimensional model, we're still resolving the orientation there.
Right. It's just not our 3D orientation. It's literally in the 1D. It's just kind of like left or right. It's just
right. And it's only the part that we were able to do this on this movement on, right? Because the rest of the cable is all mishmash. But as I'm running it through my fingers, I'm not looking at it, I'm just running it through my fingers. I know the orientation of that. And in some sense, that orientation is applied to the entire object, even though it's not really, because the rest of it's dangling someplace.
Right.
I think it falls out naturally. It's kind of cool.
Yeah. Okay. Sorry, we can go on.
That's a good question. It's a very good question with the orientation. But it's there. I think our models, the orientation model, still works. The movement along that dimension is based on the orientation and everything.
Yeah.
So during learning, are we always going to be running all these like 3D, 2D, and 1D models, trying to learn from, trying to build 3D and 2D and 1D models all at the same time? Or is there like some heuristic that tells us we should be using only 1D here or 2D?
That's a great question. Another thing we observed a lot is that our models tend to be these lower dimensional models. Like I said earlier, if I think, what's your model of a t-shirt? It's probably a two-dimensional image of a t-shirt in its flattened out form, right? I suppose I can learn a three-dimensional model of a t-shirt, and if I was on somebody's body and was touching it all over or something like that, I don't know.
Yeah.
And the same thing, like faces, right? We don't really learn three-dimensional faces. We learn 2D projections of the face. And the same with a cable. I don't think, when they show this cable on the box, and we had a box with a cable that came in because someone ordered some cables in London. They show it stretched out straight with a little like break in the middle, saying there's more of it I can't show you or something like that. So we present these and we learn them in their canonical form, just like we learned the logo in Word in a straight on 2D presentation, no distortions. And after we do that, so then we get this like lower dimensional model in our head, and then we do distortions from it.
But yeah, I think in terms of like Monty architecture or columns, it wouldn't be like the learning module itself could be like, oh, now I want to get input from 1D movements, and now I want to get 3D movement input. It would be more like some columns or some learning modules are connected to processors that send 1D movements, and some are connected to ones that send 3D movements or 2D movements, and all of them get input at once. And some of them, if we're moving on the cable, the 3D one will be pretty useless. It might learn kind of a temporary, in the hippocampus, you might learn a temporary arrangement of that cable in 3D space, but recognition would only happen in the 1D cable. But then I think there would still be some heuristics of which policy to use at what occasion. Like on the cable, you'd probably want to follow the cable, or on the t-shirt in the dark, you pick the heuristic to move along the seam. But
Yeah, and I think
nice.
some of them.
Go ahead, Nils.
I was just to say that in terms of like when they would receive inputs, I can imagine that some of the lower dimensional ones would kind of either get a displacement or not based on what is movement is actually happening. So as in like if your eyes are kind of jumping around a scene, then maybe you're not really getting much 1D or 2D. Like even columns that normally get 1D or 2D input, they're basically not getting any displacements because there is no meaningful displacement in that kind of space. It's only when that can actually be kind of estimated that they would pass that on to a column. And so I think that would kind of prevent you from constantly trying to learn like 1D or 2D models in instances where it just doesn't really make sense.
yeah,
It seems like this requires a little bit more thought, perhaps, but I would prefer if there wasn't a choice. The system worked the same way all the time, and
Yeah.
and I'm not sure we can't do that.
I think
Like,
it does. I mean, in what ways there a
maybe
choice?
wasn't there a choice like, oh, when do we go do this drop down to a lower dimension, and when don't we? It was a question
No,
or something like that.
well,
Oh,
what I would
sorry.
say is there's no choice. It's just like it's not like learning modules have multiple inputs to choose from. They're
Right.
connected to one thing or another, and then either they can do something with it or not. The only place where I think there might be some choice is on the policy side to pick how you're going to move on the object. But like this, like it wouldn't be like multiple of these would be connected to the same learning module, and then it picks which one to use at what time.
Right.
Can this be also related to object categories or object classes? For example, for the t-shirts, learning the 2D version is kind of learning the model class. Like we're learning something intrinsic about the t-shirt and something that doesn't change. But when we also learn the point clouds for the various t-shirts, we're kind of learning instances of that t-shirt at the same time as learning what makes a t-shirt a t-shirt. Just kind of jumping to like another topic that we talked about before.
I mean, yeah, I think it might help a little bit just in the sense that, as you say, these are like more kind of invariant. So in some sense could apply to more instances. But yeah. Yeah, like it definitely makes it easier to define something like a class for a t-shirt. But like I guess your favorite t-shirt you might also learn as like a lower dimensional model.
Say that again. Your favorite t-shirt you learn.
You might also learn as a 2D model.
Wouldn't. I thought the t-shirts. Okay,
At least
Yeah,
like
I agree.
with your logos on it and stuff like that. Like
You wouldn't actually learn many morphology models of t-shirts in general.
yeah.
Like an instance of a t-shirt wouldn't be crumpled in this way, and then another instance is crumpled in that way, and then another instance is crumpled in this way. It would be more like an instance of a t-shirt would be one specific surface map of this logo and text on a t-shirt, maybe. But yeah, I think the topic generally is related to object categories. And
yeah, I don't know if we discussed that much in London. I don't remember that. Did we talk about categories in this context?
a bit with the problem. I can bring it up now, maybe.
Okay.
If there are no more.
No, I have one more question. No.
Okay. Yeah, go ahead.
It's just more like a high level question that maybe ties things together, but can we consider morphology to be a lower dimensional model of a behavior? As in, you drop the time dimension and you're building a canonical model of, you're removing that variability of the behavior, like a stapler opening and closing. It's just,
those words sound like a great idea, but I'm trying to really understand them.
yeah.
It's like, yeah, that sounds great, but what the hell? I'm trying to think through it.
Just you're not dropping a spatial dimension, you're dropping a temporal dimension.
I know, I get it. It makes sense for you to think of time as a dimension, but then I'm trying to actually work through it in my head, trying to make, okay, how would that work? I'm going, oops, it might be.
Yeah, well, we have a 1D, a 2D, a 3D, and then a 4D that includes the time.
I got it.
I'm not sure it would work,
but
because time isn't really a metric dimension like the other ones. Like you
right.
can't move forward and backwards and diagonally through time and space. At least
I
not
could play
normally.
back things in my mind.
I'm not clear. It's not clear to me also that how you drop time. It's like, I don't know, time is it's always there. It's like you can't get rid of it. I don't know.
Yeah, or I guess it's more like, what would it mean? Because like here we have the specific problem we're trying to solve is to be invariant to distortions in higher dimensional space by modeling in lower dimensional space. So it feels like the analogous problem would almost be like trying to be invariant to changes in time by modeling without time. But it feels like either time has no effect on anything, and then you don't learn it with time, or time does have an effect, and then you learn to behave. I don't know. I'm trying to
I'm
think.
having trouble. I'm
Yeah,
trying.
the analogy
What is
of like the problem that we would solve.
what is a spatial model that was a temporal model that I dropped time out of? Like, it's
Right.
like, it'd be like taking a melody and okay, just all the notes collapse on top of each other, like some kind of point cloud, maybe. I don't know, but it seems like it doesn't. I don't know how that's going to work. It doesn't. It mathematically sounds brilliant, but I'm struggling to figure out how it works.
Yeah, it would kind of, it would be like a collapse. Like, I don't know, the stapler, it feels like it would be like the stapler in all of its configurations, but that's like a single model superimposed or
Right,
something.
right. How do you
And
do
then,
that?
and so that model cannot tell you what position you are in stapler
Yeah, I
time.
think it's because we think of of a behavior as a sequence of things that are like it's a sequence of some keyframes or something that changes in a specific way. Sometimes I think of behaviors, and this is probably not correct, but sometimes I think of behaviors as just variability on top of a canonical model. So that's it's like
But
we're getting rid of this
that's
variability,
but
but it's not really time.
almost all the examples we have are time based, and
Yeah,
and it's really hard to get rid of them. Get rid of it. Just I
right.
can't imagine how. It's an interesting idea. I think it's worth noodling over a bit more, but in my mind at least, like it's like, can I do that?
Yeah.
Yeah.
One more constraint around 4-dimensional is you start getting into every point as far away. And so when would you ever run across the same point in order to learn it in the first place? Once we get into like four dimensionality, like you're just the more dimensions we add, the sparser things become. And 4D, it starts the curse of dimensionality starts to become a problem, right?
But if one of those dimensions is time, it's not as bad, right? Because time only goes one direction, one way, and it's always contiguous. You can't jump ahead or go backward. It just seems like it makes it a little bit easier.
Yeah.
If you had true four dimensions, and as you point out, everything gets closer and far and everything, or you can't tell how far it is, or something like that.
Yeah, I mean, yeah, I would think of it maybe like Neil said, it seems like time isn't really a deformation that we want to be invariant to. So maybe there are some use cases where we want to be invariant to what happens in time, but I can't think of it right now.
Yeah, me
But if
neither.
there is a use case, then yeah, I think the solution would be to abstract away the temporal dimension and store
One of the
everything in
things,
3D model.
going back to melodies again, I did some experiments with this a long time ago. If you're constantly changing the tempo of a song, it's almost impossible to recognize it. If you change it significantly, rapidly, like if you crumpled up time in a song, it's not recognizable anymore.
Yeah.
That was my conclusion. It's so inherent to the nature of things. And of course, there's songs that have the same sequence of notes, but a different timing. You recognize them as different. Anyway, it's an interesting idea. So you're going to go on to problems now? Oh, Dale, you had a question.
Just a maybe an observation that I'm not sure this makes sense, but isn't movement over an object mapping its morphology onto time? You're making
Well,
an observation.
no, because if you're moving your fingers over an object, then the time isn't really important because the structure is the physical structure.
That's what I mean.
Right. But so time doesn't really play an important role there. So maybe I
Right.
misunderstood your question.
So we can drop the time from the learning model. You're dropping into a lower
Right.
dimensional space.
Well, our morphological models say have no time in them. So that
I think that's what Dale is saying, that that's an example of where we are abstracting away the time
oh, I
dimension.
see.
We're
Right.
not
All right.
storing the sequence in which we
Right.
move the
Oh,
hand.
sorry.
So
We're
yeah, I think that's a good
We're
example.
assuming a rigid model that doesn't change in time.
Right.
We're observing it by sampling it over time.
Yeah, I guess
Right.
but I guess yeah, I just don't know if there's any like distortions in time that we're trying to, like either it can change in time and generally then we try and model it, or we assume it doesn't change in time and then we just model it in a lower dimension.
Right. And that's
I
what
don't know. It feels different in that sense that like we just go straight into ignoring that dimension. Here we're kind of simultaneously modeling it at different levels of dimensionality because of yeah, I guess this added invariance.
right.
But I think I agree with Dale that it does abstract away something important, which is we want to be able to recognize an object with any sequence that we could move over it. So
Yeah,
we are abstracting away the ordered sequence part of it and the speed of
sure,
how we
right.
moved over it.
So,
And
That's why we
important
can't do
for
it for.
generalizing.
but
Yeah.
it's also worth mentioning that the way we think time is implemented in the brain and oracle models is that if timing is repetitive, it'll learn it. Like you can learn, you can move your fingers randomly over a coffee cup to infer it, but once you've done something over and over again, you might not do it. You might play back repeated sequences. Just because you repeated them over and over again, and the timing can be used. So it's not like timing is always available, and if it's statistically correlated to something, it'll be remembered. If it's not, it's not stored. So I just want to point out, it's not like time is always in all these models. It's just normally ignored because when we do our typical movements, it's not repetitive. It doesn't
Right. And the observation that Rami was making, I was thinking was related to taking a 2D or 3D and mapping it down to 2D by realizing that that dimension isn't relevant, isn't salient for that morphology or for that model. And that seems similar.
Yeah.
You're
Yeah, I
asking,
think
how do I know?
It's only
It's
relevant when we're modeling a behavior, and that's why for a behavior we need to have multiple columns, because once you move to a different location, you need to consider time and what has happened between moving from position A to position to B. So that's why we can't use the 3D learning module to a single column to learn the behavior, and we need to come up with some shared learning solution.
So yeah, I think conceptually it is similar. What Jeff was just saying is that the mechanism is a bit different in that if the time was relevant and repetitive, we would learn it, even if it's not like there's a different sensor processing or sensor module or something that never sends time information to this learning module. It has access to time and it will learn it if it is relevant. But it will not learn it if it's not repetitive. So I think, yeah, on a conceptual level, it is quite similar that we want to drop that time dimension if it's irrelevant. But in the brain, there's a different mechanism for it.
It doesn't, and the brain doesn't have to think about it. It's just either it's relevant or it's not relevant, and it learns it or it doesn't learn it. It's not like a separate mechanism or a choice.
Yeah.
A 3D learning module, well, we say it has access to time, but it can't really model for the structure. Like it can't model a stapler opening, because it will, if it tries to model that, it's still going to model it as a 3D distorted object that is just with the features changing, but it's just still modeling it as a 3D.
Right,
Because
right.
it-
Time is handled differently in a cortical column. It's not handled the same as movement of the sensor.
Yeah.
And I think that therefore it avoids all these issues. It's not really modeling a 3D object. It's modeling a 4D object. It's modeling a 3D object, and as it's going through its movements, if they're repeated and they're repeated with the same timing, then it'll learn it. But if I think to me, it doesn't make sense to think of it like, oh, it's modeling a 4D object. It's not really.
Yeah, I think, yeah, time seems to be just fundamentally differently processed. Like it arrived different places, structured differently. It's not path integratable like the movement information we get and the location representations. So yeah, I think it would be hard to generalize this to the temporal dimension.
Right. I agree with that.
Yeah, and it can be kind of sped up and slow down in some sense, like a song, whatever. But otherwise, other than that, it doesn't distort in the same way that like 3D space does.
It is it's handled fundamentally differently, just like Vivian said. So it's not another dimension. It's this thing called time.
Yeah. So shall we go to the problem?
Yeah, I'm so happy, and now you can tell us the problems. I can't remember.
No, I mean, I think this is already really powerful, and I think the problem might actually not be that big of a problem if we take several of our other existing solutions and combine it with them. But so basically, when this does not work is when there are actual, I call it volumetric changes of morphology. So if the morphology is actually like stretching out, for example, like the t-shirt, volume of the t-shirt remains the same, and if we move along the surface, everything is still the same. For example, if you have a cup, you stretch it out, everything on it, like the distance relationships, even on the surface model, are not preserved anymore. Like if we try to recognize the logo here now, it's stretched, and getting movements information on the surface wouldn't help with that stretch. Or if you have a balloon inflating and deflating, the whole like kind of the size and all the relationships of things on the balloon would change. I wasn't able to find a GIF with balloons that have print on them for some reason, but you can imagine a logo printed on the balloon moving along the surface of
I want to keep looking at the mug, but the balloon is so distracting you can't.
Sorry. I thought it was a bit more extreme example, but yeah.
Yeah. When you're, have you said your point about this?
Yeah,
we ready?
that's
All
the
right.
problem.
You know, it struck me looking at I wish I had stopped the balloon. Looking at the mug. Thank you. It's so distracting. Looking at those mugs, what struck me interesting about it is, let's say we're following the edges, right? And earlier we said, oh, well, you know, we have the orientation of the edge we're following at any point in time. But it also maybe we could think about going along this edge and then assigning a scale to that particular movement along that dimension. In the past we've talked about changing scales of objects, and it's like, oh, we have a big cup and a small cup. Often we talk about being the exact same cup, just bigger and smaller. But we also realize that these distortions can be, as we've written about in our hierarchy paper, they can be distortions of scale as well. And so I'm just wondering if it's a general solution is that as we can assign scale to movements on a sort of, you know, a 2D movement basis. I don't know how to describe it better than that.
So that's basically the first potential additional solution.
Oh, you already voted. Sorry.
So basically, yeah, in addition to transforming the movement by the orientation, also transforming it by inferred scale. And so basically saying, okay, scale, maybe with the balloon, just normal scale would be enough. But if you like stretch this cup, scale might just be directional in one direction, like scale in the X direction, but not in Y direction. I think the place where it gets a bit more tricky is when there are different scales at different locations, like the mug kind of stretching out at the top, but getting narrower at the bottom. Because then we would have to store scale location by location and apply that, which isn't unreasonable, but it's harder to do inference on this. Like if you haven't seen this before, you'd have to infer a different scale at all the different locations.
Well, I don't know if you'd have to. I don't know. It's interesting. It feels like, okay, if I've never seen that middle cup before, I've only seen straight-sided cups. Well, I'm pretty sure I'd reckon, you know, I would see, oh, there's a cup. Maybe I wouldn't. I don't know. It seems like I would.
Yeah.
Maybe I've seen a bunch and too many. I don't know. Like the one on the right. Well, other than the fact that it doesn't really have proper 3D perspective on it, you know, and that's a novel one. And if I hadn't seen that, what I would do, it would be like the crumpled T-shirt. If I saw something really odd like that, I would follow around until I find features like, oh, there's the handle, and then I follow down the edge, and there's a bottom. And yeah, it's the fact that as I'm following the edge of it, it's curving, and it's got distortions to it. Somehow it feels like this mechanism should still work. I don't know. Maybe we have to think through it more, but it seems
Yeah,
like
so you mean
this.
as if we just go in the 2D model, the scale could be
It could be
adjusted.
applied. It feels like I'm following an edge to get from feature to feature, and if I don't travel the right amount of distance to get to the next feature, that's obvious. You know, like unless I had a really tall, skinny one, like you showed in the first one, maybe. Or I'm imagining a very tall tree. So I have this lollipop image of a tree in my head, and I see one that's really tall and skinny. Um, I would still do the same inference mechanism of following. It's like a distorted T-shirt. I would still follow the edges to get to. And somehow I would note that somehow I would say yes, it's still the same thing, even though there's a distortion in scale on this dimension. It just seems like this solution should solve this problem. I don't know. I don't know yet how.
Yeah, I mean,
Maybe,
yeah, it does seem like you could infer that scale is different by noticing, oh, the feature I expected appeared, but it appeared a bit earlier or later than I expected. And then as you move around the bottom, maybe it appears earlier again, so you infer a bit of a different scale again.
Yeah, and that might be easier in lower dimensional space because, like, if you're in 2D or even 1D space and something arrives too early or too late, it's easier to kind of shrink or expand to sort of match your expectation than in 3D space.
Yeah.
Um,
this is very close to the t-shirt problem, and it's just as you point out, it's stretching a bit, right? It's stretching on these dimensions, and we tend to think of a t-shirt as, unless it's an old t-shirt, we tend to think of it as more. It doesn't. We're assuming it doesn't stretch. We assume it's got its shape. But then I
Yeah, it's
have
maybe
t-shirts.
like the example you gave during the week, that if you suddenly have like a t-shirt from a tall basketball player that's very
Right,
long,
right,
you can
right,
still recognize it as a t-shirt.
right. I have t-shirts that are longer and shorter, depending if I went to the effort of getting an extra long t-shirt. They fit better, and so some are long and some are short. And I never got confused by that. It's like if I were running my finger down it, I would say, "Oh, this is the longer one, or this is the shorter one." Um, Anyway, so all I guess I'm saying is it feels to me like the mechanism that we've identified for this this sort of edge tracing in a reduced dimension um, should work here. And if it doesn't, we have to just tweak the algorithm, and maybe you know, yeah,
Yeah. And so, yeah, that was kind of my main takeaway in the end as well, that it seems like, yeah, the main mechanism is quite powerful already, and potentially just taking the existing other things we have might solve the rest, like scale. So,
right,
yeah, if
right,
you don't mind, I can just go through the other potential ones, and I think
sure, sure.
some of them might complement it a
Um,
bit.
Can
Yeah,
I
sorry.
mention
Okay.
like one example of this that I thought about is like stretching a rubber. Let's say you have a rubber glove and you pull out one finger. That's a very local kind of deformation. It's not really like stretching the glove at all, like not at all fingers, but you're just pulling at one finger. That is a case where the model of the stretch glove wouldn't match, the glove itself intrinsic in 2D or 3D. I guess those are the kind of issues that I saw with. I mean, I think that I agree. I still agree with you that you can still solve it with other things, but not necessarily about the
That's an interesting
representation.
example. That's an interesting example, but it seems somehow different because, like, the rubber glove always goes back to its
I'm talking about
position.
one that doesn't go back. Sorry,
Oh,
like
well,
that.
then it wouldn't be a rubber glove. Then it'd be some sort of magic glove that's unraveling or something.
Or kind of clay. I don't know. I think clay
Okay,
was a
Clay.
good. Yeah.
All right. Well, you started with a rubber glove and you're stretching it out. So I was working with that one. Well, but that is an interesting question because there's something it has this. It doesn't really. That's almost like a behavior of the glove that you can stretch it out in certain dimensions,
Yeah.
and it'll go back typically. Um, if I saw you holding a glove and pulling on one finger, I wouldn't think much about it. But if I just saw a love glove lying on the table and one finger was twice as long as the others, I go, "What the hell happened there? That's really weird." Um, and
Yeah.
I'm not sure what to make of that.
Anyway,
Yeah.
just
Yeah,
throwing
I
that
think,
another example.
I
Yeah, it
guess,
is a good
yeah,
example.
one thing I was thinking in this case, there could be kind of location by location scale that you could either infer, like saying, oh, at this area, the scale seems to be different, or even store if you're learning a model of your stretched out glove that has a particularly long index finger. Can, yeah, maybe storing that, but not
Hmm.
sure how location by location scale changes could work in practice.
It's yeah.
I mean, I guess at least in inference, it doesn't seem that difficult because most of the relative features on the glove would still be fitting the glove model. So you'd be able to tell that this looks kind of like a glove.
Yeah,
And then
like a
only once
partial
you get to
match.
the finger, you see, oh, here scale doesn't seem to match what I inferred for the rest of the glove.
And
But
if
you
if you have a
probably should.
child object representing a finger of a glove, then you could kind of apply it globally, maybe at that object.
Yeah. I mean, I
Yeah.
think there's probably in the future. I mean, I think we like very briefly discussed this. We probably need some learning of like material property. There was like talks about fire or clay or
Maybe,
rubber
but I
or
think
not.
the glove with the weird finger sizes is no different than a tree with a weird limb size. I mean, it just seems that the world is full of objects that we classify, but almost all of them are unique,
Mm,
right? And so I think the glove example, if we're talking about not one that stretches back, but one that just has a long finger, that's just in the class. That's like a cup that has a bigger handle, or a tree that has a bigger limb, or these are all the same thing. So I think it's a good example to throw into our mix of thought experiments. But I sense that that these are all solvable in this mechanism, and as Vivian's going to show us how.
All right,
Yeah.
sounds good.
So
Let's go.
yeah, definitely leveraging scale can be part of the solution and help a lot with those extra problems. Another part of the solution could be to learn separate morphology models for different distortions. So for example, with trees, you might not just have one morphology model of a tree and then have to account for all the possible distortions of trees, but you could learn several morphology models of trees and then find the closest one to that, and then only account for slight modifications from that one.
Right.
So
we came up with the example. We came up with the example like, if you draw an evergreen tree or like a Christmas tree shape, that's different than a lollipop tree shape versus, we even children have multiple morphology models of trees.
yeah. And so, yeah, saying we're going to learn multiple morphology models at first maybe sounds expensive because we need more models, but probably wouldn't be, because we can still project many kind of 2D feature maps onto those morphologies. Like you can still have the Christmas tree shape with many different decorations on it, or different leaf colorings on the lollipop tree and all that. So it doesn't seem too much of an ask to learn a couple of different morphology models. And then, yeah, this wouldn't solve the issue of surface features distorting with the morphology. So like the logo distorting with the cup or on the balloon as it inflates. It wouldn't, like if we just learned a separate morphology model for these three cups, it wouldn't tell us like how the logo on it should distort.
Well, it's interesting because in reality, if I had those first two mugs, or in all these, if these mugs really existed in the world, the logo probably wouldn't be distorted.
Yeah.
We would have printed the standard logo on it. Interesting. I don't know what to make of that, but I'm just.
Yeah, I guess
So-
it's more about like we can recognize these distorted versions of the logo, like independent of the mug too. So it seems
Yeah,
like there's a
right.
way. I mean, maybe that's again just scale. So maybe that's not an issue at all. But yeah.
And even like the middle example, I feel like I'm just the sort of like model-free suggestion of depth is kind of making me think, okay, it's just like a logo on like a vanishing surface, and
True.
I'm kind of accounting for the distortion by like basically the 2D movement, at least in
Yeah.
that case. I know that doesn't apply to all of these, but um,
Yeah. But
and
yeah,
of
I
course,
think about
yeah,
it
the
a
the
bit
other
more now. I think scale can
yeah.
probably already solve that part of it.
And it helps again if we don't expect ourselves to have like a perfect solution, like in the sense that like humans don't like perfectly model this and say like, oh, what the heck, this thing is slightly longer than I was expecting. Like
Right.
those things all just look kind of weird. And then, but yeah, we just kind of recognize that something's slightly off, and it's the scale basically.
Yeah. Okay, so yeah, those two in combination with the lower dimensional models, I think already solve quite a lot. I'm not sure if we need more. One other thing just that we discussed before is a potential solution could be to learn models of how an object can distort and then apply the stored changes to incoming movements. So this could be kind of like the behavior model of squishing a ball. And then we take the changes that are stored here and apply them to the incoming movements to account for distortions that happen.
What, to predict what the shape will be when in a
Right, to
behavior
predict,
model?
to be on the correct location in the morphology model, even as the ball is distorting.
Mhm.
Yeah, that would be kind of a location by location model based solution. And then lastly, another one we talked about was using an abstract or relative, but not metric arrangement of features. And I think we weren't convinced by it, but just put all the options we wrote down last week, which was, yeah, basically as we go over the mug, another type of sensor module might not tell us at all anything about distances between features, but just relative arrangement of features. So just whether something is above or below or to the left or to the right. And so, yeah, it would just say rim is above body, is above bottom, and then the handle is on the right. But yeah, that would likely not be very good unless all possible edges are learned, since
right.
path
I imagine
integration is
that.
possible.
I don't remember, but I imagine I didn't like this.
Yes.
So good, I'm
Yeah,
consistent.
this came mostly up because of like the idea of like learning a family tree where the
Yeah.
length
Yeah,
of
like a
arrows and
squash
distance
card.
between them doesn't matter. It's just about the kind of abstract arrangement of them being above and below. And yeah,
Yeah. Although I could argue that family trees really do have a morphology, and there's, you don't expect the connections between the people's names to be, you expect them to be within some range of lengths. It's not like, it's not like I expect there to be a line of certain dimensions there, and it could be longer, it could be shorter, but it's not like it's not like I don't know that there's you know, a connecting line
I
between
mean,
them.
I don't know, because like, as in, yeah, there is like a normal family tree that maybe in kind of higher two-dimensional space you have a kind of model of. But if someone drew on the floor like dad and then this long arrow going all the way across the floor to daughter or whatever, like you would understand in abstract space that like that is a single arrow that's just connecting those two concepts like a family
Right,
tree.
right, but I don't think I have a model of it that way. And family trees can be horizontal and they can be vertical. So you
But
have to be really
that's kind of the
careful.
whole point, I guess, is that that would,
Um,
in the same way that the lower dimensional models kind of abstract away the kind of spatial metrics in higher dimensions, an abstract model would abstract away kind of unnecessary
so
metric
I
details.
don't I'll say it again, I don't like this idea. So, but here's the alternate way of doing it. This goes back maybe to what we were saying a slide or two ago. Imagine I pick up the t-shirt and I feel the edge of the collar. All right, so now I'm gonna, or maybe the edge of the the edge of the um, sleeve or something. I'm gonna follow. I'm at the edge of a collar, and I'm gonna move my hand along to get to the other side of the collar. So I'm gonna follow it along the ridge of the collar and get to the other side. Now, if it took longer, I'm doing this in the dark, so I'm not looking at it. I'm just feeling it. If it took longer to get to the other side, I had to go further and say, "Wow, this shirt's got a really big collar. Maybe it's a comical shirt or something like that." But now all of a sudden, imagine the entire shirt really big, because I've only moved along one dimension from the left side of the collar to the right, and now I'm saying, oh, this is really big, or maybe I'd say it's really small. It's for a doll or something like that. But my image of the entire shirt has now shrunk in a shape. It's shrunk. But now if I went down vertically along the seam from the collar down to the hem at the bottom, and that one was much longer than it should have been. Um, it feels like every time I traverse one of these edges between features, I have an expectation of its length, but if it's different, that's not a problem. I'll just say, oh, right, that one's longer than it should have been. This is shorter than it should have been. I guess I'm saying it feels like the same mechanism is involved. I don't get rid of those edges in the graph. I don't. It's not just the relative arrangement of features. I notice the distances, and I will temporarily remember those temporary distances. I guess I'm saying I'm trying to walk through mentally doing this, and I don't think there's ever a point where it's just the arrangement to me. Feels like the edges of the graph and the lengths of those edges are important. We're
yeah,
doing
so
research
more of
here.
a local scale solution.
Right. That feels like the right thing to me.
Yeah.
Right.
And yeah, with the family tree, it might just be that the abstract space in general has different movements, but we don't need to use that solution for
Right.
physical objects.
And my grandmother did family trees, genealogy for a family. I can picture some of these. Some of them are quite complex on a sort of a large sheet of paper. And I imagine if I took out the lines between those things, I'd have no idea what's going on. I don't even, only by reading the names and catching up the names with each other, say, oh, that was supposed to connect to this one, because those lines really are important. They sometimes go up and down, left and right, they go all over the place. I'm just
It's almost like the lines tell you the movement vector.
Well, exactly. That tells
Right.
you the movement in the abstract space.
Yeah.
But it's yeah.
But then
It's
the
not,
point is,
right,
if the line was
even a relevant
curly or if the
arrangement,
line was straight or whatever, that
because a
doesn't matter.
child in her age, some of the people had 15 kids or something like that, and going back to the 1800s, and so the children, some of the children can be just slightly lower than the parents, but much to the right of the parents. It's like it's how do I know that's important, that it's below, whereas there's other people mostly to the right. And anyway, I guess I'm just I'm expressing my my discomfort with this number 4.
Yeah, I mean, to me, it seems like for family trees, maybe the arrows are the movement vectors, and that's why it doesn't matter if it's like to the right or to the left. But then that's still not a solution for distortions of physical objects, because there we don't want to use kind of movement in abstract space. We still want to have movement in physical space.
Right. We want to move in physical space. So I think the general solution, we say we have a one or more sort of canonical morphological models for things. And then if we see something which is different that we've not seen before, we haven't learned as a new specific instance, then we're going to do this. We're going to do this dimensionality reduction trick to figure out what it is. And then we can learn a specific instance of that very quickly. We'll talk about that. Maybe, I don't know if we're going to get to that part today. The thing we talked about, the hippocampus.
I don't have
Yeah.
that today, but we can talk about
Okay.
it next week.
Okay.
But yeah, so then it sounds like actually we can solve all the distortion problems using the dimensional reduction trick, scale, local scale, and learning several morphology models if there's a wide variety.
Right.
I guess the only one we had a 5, which was the like the child using hierarchy. What was the reason you
How does
didn't
that
put
work?
it this
I
time?
remember that. What was it?
Just this is stuff we've talked about a lot of times, but just like that basically if you recognize child objects, like those will have basically you can have distortion of kind of the global arrangement of parts as long as the parts themselves are still recognizable.
Is this our
Then you can
zero?
be
Is this
more.
our 0D model that we argued
No,
about?
this is like recognizing a car, like you recognize a tire, and the point is like you can kind of move where the tire is exactly, but as long as the tires themselves aren't distorted, you're still recognizing those parts. We've talked about this in the context of like omniglot, like recognizing letters, that like you recognize individual strokes and then how those are arranged for the letter. If that rings a bell.
Uh,
I added maybe 5 use compositional models with more tolerance for location mismatches.
Yeah.
That
I mean,
captures
this will just like naturally happen with compositionality. It's not an added. It's not something we have to engineer, but it's just
right.
I think it's worth mentioning because it will give additional robustness.
I'm confused by it because it seems like, by the way, in your mind, all models are compositional models. I mean, in some sense, all models have features at locations, and the features can be other models. So, but it felt to me like with the t-shirt and the cable, you're always trying to get to recognize features. You're always moving along this dimension till you get to a new feature you recognize. So I'm not sure how that's different, I guess.
It's complementary. I mean, basically, in the example of the T-shirt, like it's helpful, obviously, to recognize a collar, and in your model, in your reference frame, you're representing that there's a collar there and then a sleeve, as opposed to just relying on like there's a cloth edge and a cloth edge and a cloth edge and a cloth edge.
Right. No, I see. I see. I don't think that works. You're right. I think in my mind, this system always requires you get to features. If I just move along, like imagine you're picking up a sheet for your bed, and you're like a fitted sheet, and you're trying to find where the corners are. And sometimes it's hard to find where the corners are if it's a fitted sheet, because they sort of go around it. And so you move it along, and you realize you've just been going forever and you haven't gotten to the corner. It's like you have to get to a feature. You have to get to some recognizable feature of this edge tracing thing doesn't work.
Yeah, that's why I didn't put it here, because I thought it was kind of already implied in.
Right. That's how I do it. The t-shirt and the cable require that there are these compositional models where there are features you can get to and recognize. Just like a tire on a car. It's a really weird car, but then I say, oh, there's a tire. Now I can move forward and see if I get to another tire, type of thing.
But yeah, I mean, I think it's still worth mentioning again that this also gives us some extra tolerance. If we're already recognizing a pretty unique feature, like a tire or a collar, that already helps us kind of narrow down that we're likely on a t-shirt or on a car.
Right.
So yeah, I think
But
combining 1, 2, and 5, we can solve most humanly reasonable distortion problems. If we needed something more complex, 3 could still be a viable option in my mind, but it is definitely more complex.
yeah, I don't think we talked about these distortions in terms of behavioral models. I don't remember.
No, not in London.
Well, yeah, not in
no.
London, but I brought them up a couple of months ago.
We didn't talk about it in London. I trust you.
Not in
I
London.
just don't. I don't remember it.
Yeah, I think we had some whiteboards here on that, and then a couple of other ones, I think. Maybe I didn't. Yeah, this one I think too. About, oh, where was it? Yeah, the distorting logo here, where we learn the behavior and then apply it to the logo. We learn a behavior model, exploding and apply it.
I don't remember this, but we come back to it maybe another time.
Okay, that's all I had on distortions. I don't know how people feel time-wise. Do have some slides on affordances, less than the others, but I don't know how much discussion will ensue there.
I'm ready. I don't know if someone has to drop off.
Okay, yeah, I think affordances were our conclusions on affordances were the least controversial, but still quite powerful. So maybe it's fun to talk about them now, if you're up for it.
Is anyone not up for it? Anyone wasted? Speak up.
But yeah, maybe I don't know if we time cap it on it, or I guess we just go for it and just see.
I thought.
Stop
I mean, in
rotating.
general, we said these meetings could go anywhere from 2 to 4 hours, right? So
Right.
Yeah.
we're at 2 hours now.
All right. Yeah, let's go, and maybe in half an hour we take a break if we're still at it. Okay, so just briefly for anyone who isn't familiar with the term of affordances, because it's maybe not that common of a term if you haven't studied psychology. I just copied the first sentence from Wikipedia, which says, in psychology, affordance is what the environment offers the individual. In design, affordance has a narrow meaning. It refers to possible actions that an actor can readily perceive. So a couple of examples. A doorknob shaped to reflect how it is used is an example of a perceivable affordance. Chairs afford that we sit in them. Grips afford that we handle them. Dials afford that we turn them. So it's basically from looking at something, it invokes an idea of how you interact with them. Our kitchen in London, for example, had very bad affordances, where you would look at the closets and they would not tell you how to use them. So yeah, is that kind of clear, or any questions about that?
Super clear. Yeah.
Okay. And so yeah, one kind of insight we had in that week was about how affordances could be represented in the neocortex. And we wrote down this definition here, which is affordances are causal links to behavior models in motor cortex. So behavior models in motor cortex would basically encode a sequence of changes or actions to send down to that can be used to send down to subcortical motor regions. So basically how to execute an action, like grasping something, pushing something, turning something.
Turning something, yeah.
Yeah. And then so the affordance would be another model somewhere else in cortex, like visual cortex, for example. This could be a behavior model or a morphology model that has a causal link to this behavior model. So for example, seeing the door handle invokes the behavior model of grasping and pulling it down, or seeing the dial invokes the affordance, the behavior model of twisting it. And so this green connection, if you remember from our last brainstorming week, those are the ones we drew from layer 3 to layer 1 to be used as learning causal relationships, both forward and inverse causality. And so in this diagram, it would be this connection that goes from the behavior model of the rocker, like the visual one, to the behavior model of forward pressing that can then be executed by your finger. Yeah,
just seeing a particular morphology model automatically invokes the thought of doing it, of touching it or rocking it or turning it.
Yeah. Yeah, exactly.
You don't really have a choice in the matter. It just, you see it and you think of it.
Yeah.
Doesn't mean you have to do it, but
so yeah, I wasn't sure about how to order these slides, but here are just a couple of points, a couple of elaborations on affordances. So one nice extra idea we had was that for generalizing affordances, so to have less object-specific affordances, we can learn general affordance models. So basically, in order to not have to learn a morphology model of every door handle you know about and associate that with pulling it down, or an affordance connection from every box that you could pick up and learn an association to picking it up behavior, you could have a kind of more generic affordance model. Mechanistically, it would be exactly the same as a behavioral morphology model. Nothing different there. It's still features at locations. But basically, they would be learned by only attending to locations where actions are applied. And that could either be observing someone else applying actions there or applying the actions yourself. Like you could see someone pick up this box or pick it up yourself. In both cases, you only pay attention to the locations where action is applied, like here and here. And then the model would just be a surface here and a surface here at that relative distance. And whenever you then again see a flat surface here with a flat surface over there at this relative distance, you know how far apart you need to space your fingers and which grasping behavior to execute. It doesn't have to be this particular box again. It can be any object that has two opposing flat surfaces.
in some sense, the affordances become a child object of the box, right? It's its own little. It's those places where the fingers are touched. Those are the places where you have a model where you associate those places with the morphology of those two surfaces with grasping.
Right. Yeah, you can learn it
as
a child feature, but you can also recognize it on a totally novel object. Like you can see a box you haven't seen before and still recognize that it has these two relative features.
Right, but wouldn't that be, in that case, those two relative features are its own model, right? It's like a child of a box. So if I see any box where I have two parallel edges not too far apart, I can recognize, if I attend to those two edges, I can say, oh, that is a grippable area.
Yeah.
I can imagine
exactly.
gripping it.
I'm just saying, like, You don't need to have seen that's why it generalizes so
No,
nicely.
but I'm saying
You
it's
just
a
see
child it's a child object of the box. It's not just two locations on the box. It becomes like a child object
Yeah,
of the box.
this is its own model, and this is what
Right.
would have the affordance connection to the behavior model of grasping.
Right.
So I'm a little confused. Is affordance an explicit model that's learned in its own column, or is it just like the association between like some morphology and the
Both. It's a on the left side of this diagram, it could be a specific model like a button. Well, go back to the previous diagram. Oops.
previous
The
slide?
previous slide. It's the previous slide. Sorry.
This one?
That one. Yeah. Right. So you could learn a visual model of like in the case of the box, you might have to learn a new sort of child of the box, which is these two parallel edges, and so you'll see that that's a sort of separate model, and then it's associated with the behavior model. So it's always the affordance always has this causal link, the green arrow here, always. You have to have that. And then on the other side, there's going to be some behavioral or morphology model, and that could be a new thing that you like. There may be something you never noticed about an object until you see someone touch it in a certain place or certain way. Then you say, "Oh, that is now a new child object or a new thing that I have to recognize." Where were the fingers touching? I may not have had a correct morphology model for that already. If that's not clear, I could give you some examples.
Yeah, what was
Yeah.
a question just about like the terminology, Rami? Like, what are we calling affordance?
Yeah, well, I was just wondering if there's an explicit model. I think what Jeff is saying is that there would be. We could learn a model of these, like the two surfaces or the two edges of the box, as an explicit model in the visual cortex, and that would trigger the behavior model in the motor cortex.
Yeah,
Right.
so we could have a direct affordance connection between the specific morphology model of the specific box.
No,
But we can also
yeah.
learn this more generic affordance model. And this one is basically just a standard morphology model, only that we just paid attention to the locations where action was applied. So yeah,
And
it's
then the
not
idea
a,
is
not
that
a
that
different
can be
kind of model.
reused much more.
Yeah.
Because it applies to many more instances that we'll see. Like basically any instance where appropriately enough you can apply this affordance.
Is there a signal that triggers the learning of this generalizable morphology model for triggering
Yeah,
that?
so what we kind of talked about was that when you are interacting with something, or maybe when you observe someone interacting something, you attend to kind of like where they are interacting with it. So literally where these pink dots are. And so that would help you form this kind of more sparse model.
Okay. Yeah. So it's like
Yeah,
at
just a
the
couple.
fingertips or
Yeah. Yeah, maybe it helps if I just fill in a couple more of the details to add some more context. So a model, a behavior or morphology one, can have several affordances. For example, this model here, or even the model of the box, could have the affordance of being grasped with the right hand or grasped with the left hand, or something could also have the affordance of being picked up with chopsticks, or a button could be pushed with index finger or thumb. So yeah, you can have several of these green causal affordance links for one model. An affordance is learned by observing the co-occurrence of a model with a behavior, kind of the same way we previously described learning these green connections. And then I put this in air quotes, the affordance models, so this kind of general one, because it's just a standard morphology model, can be associated at locations on other models. And that's what you mentioned, Jeff. It becomes a child object on that specific box. But it doesn't have to be, like, it can just be recognized based on the sensed features on a totally novel box during inference. And when wanting to execute a behavior, we can use priors to look for the corresponding affordance. So I want to twist something, I can look for the features that are associated with twisting, or if I want to turn something on, I can look for the affordance of a button. And models that have affordances can also be compositional objects. So if you can't execute the affordance, like you want to pick something up, but your hands are tied or whatever, you can pick it up with your hands. You can try executing the affordances of child objects instead. So that kind of makes it, that's one of the other powerful generalization points of this, where we have the affordance model of grasping, which are these two things, and the affordance of that would be executing a grasp with your left or right hand. But then if that's not available, this could be composed of child objects, each just representing one of the two surfaces and being represented with being associated with the behavior of applying force to that surface. And so then we could use other tools like chopstick or prongs or something else and apply force at both surfaces in sequence to kind of solve that problem if we don't have the complete one available. And that would also be how we could learn kind of compositional behaviors that we haven't executed before.
I was thinking this problem of generalizing of like which hand. This would be a generalization on the other side, in the motor cortex itself. It feels like we have two
Right.
types of generalization. There's the like on the motor cortex. There's the whether you apply left hand or right hand or whatever, and on the left side with in the visual cortex, um, uh, we're generalizing by just getting those edges or surfaces where we're applying the actual action. So it's like whether we want it to be in a box or a jar or something like that. So we're generalizing the model that we apply to in the visual cortex, that we're generalizing the actual motor action, or like what end effector to use that's in the motor cortex itself. Does that make sense?
Yeah, as in the motor cortex, you could have a hierarchy as well, almost like of abstraction. So like you have the kind of grasping with your hand, but maybe you have like a kind of grasping notion that's associated with many grasping with your right hand, grasping with your left hand.
Yeah.
And you just make the association. Yeah, I've also leaned towards that, but I think you could kind of have both happening in parallel. At least that this is already going to get you a lot of generalization because the visual models are going to be so reusable. Whereas I guess we don't have a concrete way right now of developing abstract kind of motor models, but I think it could be useful.
Right. I think it's a good point, Rami. I think that what felt like a really big insight here was just this several components, that you're always going from some sort of morphological or behavioral model that's inferred in like visual or touch somatosensory cortex. You're then causally linking to that to a behavioral model in the motor cortex, which is just another type of model, it's just another type of behavioral model. And that when you generally have to observe someone do this, or you could do it accidentally yourself, but generally you'd observe someone else do something. You see where they applied, you recognize the behavior model that they're applying to some object. And then you now establish that link, and you can say, I can do that too. I can put my hand there and push these buttons, or I can grab it and turn it. So, I mean, these are the components that felt really powerful, I thought. Just very simple.
Yeah,
So now we're talking about these. Now you bring up these subtle issues, which are good to think about. Like, oh, is it hierarchical on the motor side and hierarchical on the object side? Yeah, that's a good question.
it could be very rigid in terms of like not generalizable. Like I could see someone doing something with the right hand, and I would think that I would have to do it also with the right hand. But if I have a model,
Right.
how does it generalizable?
Obviously, we don't want to do that. So we'll have to make sure we don't do that.
Right.
But the way of like breaking it down into the child affordances, I think, solves it, because you just need to apply force to these two surfaces, so you can invoke any potential behavior models that are connected to those, so you can pick it up with your elbows, for example, instead, even though you've never done that or observed that yourself. You just know that you can apply force with your elbows.
What if I want to generalize the full grasping action, or like pinching or something? Like I agree that there's a hierarchy there, and this also could happen in the motor cortex. Like
I mean,
breaking.
it might. I mean, I'm not sure. Maybe you could, but I feel like we're actually not that great to generalize to the other hand. Like, I'm much worse at doing stuff with my left hand than my right if I don't practice it a lot. So I'm not sure we can assume that they just both learn the same things, but maybe that's subcortical.
I mean, it's so, just thinking out loud here. Imagine there's a button and you see the little circle with the line through it that indicates an on-off switch, right? And maybe it's not even a physical switch; it's just an indicator, and you just have to touch that icon. Obviously, if I see that, my first reaction is to reach out with my right finger, my index finger on my right hand, because that's what I'm right-handed. That's what I would do. But obviously, I could touch with any finger on any hand. I could touch with any object, perhaps. This is capacitive sensitive. So it seems we have to solve all those issues. But I think Vivian was getting at the basic idea. There is like, okay, somehow we have to generalize. We have to generalize. I agree with you. We have to do that. So we have to be able to say, what other ways can I touch this thing? Or what other ways could I grip this thing? Or, I don't know if we have a solution to that completely right now, but
Yeah,
but
I guess
but
those are good.
the things we did talk about, I think, are pretty rock solid.
Yeah.
The causal link.
Quickly, wrap up the advantages, and I can pull down the slides and we can go into the discussion. But because there are some great advantages of this insight. So having these affordances means we can recognize potential ways to interact with novel objects that we haven't seen before. We can invoke learned behavior models in the motor cortex. We can generalize to novel actuators by breaking down compositional models and invoking child affordances. And so, it feels like a pretty general purpose and nice mechanism.
And then the other thing is that, maybe just reiterating again, the affordance may not be obvious at all until you see someone do it. And only then do you recognize, oh, there's this thing that's now an affordance. Before I didn't know it was even there. I didn't even notice it before. So it's sort of by observing someone doing the behavior, you then learn a model of the thing that generates that behavior.
Right.
Yeah, and it also kind of maps, I think, well onto the anatomy in terms of like motor cortex is often described as agranular because it doesn't have a layer, or it has a very little layer 4 that kind of disappears over time. And it makes a lot of sense in this kind of setup because all the inference is happening in other parts of cortex in terms of recognizing things in the world that are then invoking motor cortex. The job of motor cortex isn't to, in that case, to kind of infer, recognize things. It just needs to kind of have these representations that can influence subcortical stuff.
In the meeting, we went a lot further than this. We talked a lot about how you would know how to move your hand to the right location. Like, okay, so visual cortex says, hey, there's a switch at this location in the world. And then your hand may be someplace else. And how do these things communicate? Because your hand has to move to that point. And we spent a lot of time on that. I think we made some conclusions. I don't remember, but it felt pretty good.
Yeah.
We spent a lot of time on it.
Today I basically covered this part here. Oh.
You just covered it. You just covered it. Good job.
Yeah, I literally covered it. Then the voting part here, and kind of shared learning by implication, which both of them, like you can see, still have some open questions, the red parts. And then the affordances one, which feels like they were actually no big open questions, or at least it was the most solid one.
Yeah, I thought it was pretty good.
And then, so yeah, Niels and Jeff, if you want to cover the rest next week, I can try and put together some. I think larger parts like these parts will just turn into more brainstorming discussions and trying to figure
right.
those out. But
I'll just say
yeah.
one of the things, I mean, it's all exciting. But one of the things I was really excited about was at the very end. I mentioned earlier, we didn't finish it, but we were talking about how the hippocampus interacts with the cortex. And because we're constantly learning new things, and our assumption is when we learn anything new, it's in the hippocampus, but we're relying on previous knowledge all the time too, and that's in the cortex. And so we had some ideas about how these two work together. And so when you're learning something new, you're associating new features in the hippocampus, but associating with the existing knowledge in the cortex. And maybe I could do a diagram for next week on that.
Yeah, that would
Just
be
talking about
great.
that.
Yeah, I got that topic here.
I said maybe.
And
We'll see. I'll try.
but yeah, I definitely plan to go over that topic next week. If you don't get to it, I can try and make a slide about that.
We'll see.
And then, yeah, we still have the whole idea of target pose and goal state and how those could be communicated subcortically and between columns, what the output of L5 would represent.
Yeah, right.
Yeah.
Yeah. Yeah, and we had some, I guess, like excited conversations about that, but it wasn't clear that we had like a solid, especially because like we went down one avenue and we're like, oh yeah, this makes sense, and then it's like, oh, but we just decided we're going to output displacements and not locations, so that means, yeah,
After we could get a little drunk and everything starts looking like a good idea. Yeah. That's a great idea. That's a great idea. The next day you wake up and go, oh my God, what was I thinking? Oh.
Yeah, I think we can definitely use a lot of the other topics as kind of starting points for further brainstorming.
Yeah.
Because yeah, we also wrote down just kind of the full step sequence of learning how to output actions, and that could be a good starting point, and then going into the
right.
brainstorming on the details after that.
Cool. Yeah, thanks,
Okay,
Vivian.
yeah.
That was really helpful.
Nice summary slide. This is really great.
Thanks.
And also great points from everyone else.
Right.
'Cause one of the things
Yeah.
we were looking forward to was, yeah, getting feedback, but also new thoughts from you guys when we came back.
Right. There was a lot of good ideas and good questions and good everything.
Okay.
Anyway, it still seems pretty exciting even 2 weeks later.